In this video, we will look at the relationship between the chemical potential and concentration, as well as colligative properties, the elevation of the boiling point, and the depression of the freezing point. So we have seen in the previous videos that the chemical potential of a solute, let's say B, depends on the chemical potential of the pure solute plus RT logarithm of the mole fraction of B. Now, the mole fraction of the solute must be proportional to the concentration of the solute. This could be a molarity, for example. So we can write this as xB is equal to some constant multiplied by the concentration, or it could be another constant 2 multiplied by the concentration divided by a standard concentration. This could be 1 molar. So we could write the above equation as mu B, the chemical potential of B, is equal to the chemical potential of pure B plus RT logarithm of this constant, let's call it K, concentration of B divided by a standard concentration. We can split the second term and write this as mu B star plus RT log of K plus RT log of the concentration of B divided by a standard concentration. This term here can be combined as some standard, because K is a constant, some standard chemical potential plus RT log of the concentration of B, assuming that C is equal to 1 molar. So the chemical potential can also be written as in terms of the concentration of B. Now let's say you have two compartments both containing B at two different concentrations. Here the concentration is B1, while here the concentration is B2. If I want to find the difference between the chemical potential in the two compartments, delta mu, we can write this as mu B1 minus mu B2. And this is equal to, if I substitute in the equation above, the standard chemical potential will be the same for both compartments, and then we'll have the concentration of 1 minus the standard chemical potential plus RT logarithm the concentration of 2 in the compartment 2, I'm sorry. These terms cancel out and we eventually get delta mu, and now I'm removing the subscript. B is equal to log of the ratio of the concentrations in the two compartments. This is an important relationship, particularly for cellular systems, because we are often interested in the gradient of chemical potential across a cell membrane. So this was part 1 of this lecture, which talked about the relationship between chemical potential and concentration. In the second part, we will look at colligative properties. Colligative properties are properties of dilute solutions which depend only on the concentration of the solute and not on the identity of the solute. And the colligative properties arise from the fact that if you dissolve a solute in a solvent, the chemical potential of the solvent is reduced. So we know that mu A equals of the solvent equals the chemical potential of the pure solvent plus RT logarithm of the mole fraction of the solvent. Since the mole fraction is always less than 1, this quantity is always negative. Therefore, the chemical potential of a solution will always be smaller than the chemical potential of the pure solvent. Let's try to look at this a bit more graphically. If you remember from the fundamental equation of chemical thermodynamics, the partial derivative of the Gibbs free energy with respect to temperature when keeping the pressure and composition constant is equal to minus S, entropy. Since entropy is always positive, this value, which is essentially the chemical potential, the gradient of the Gibbs energy with respect to temperature, is always negative. So if I draw the chemical potential on the y-axis and the temperature on the x-axis, and we take a solid, the chemical potential will vary with temperature, something like this. So this is for the solid. For the liquid, the entropy is a bit higher, so the chemical potential is likely to look like this. For the gas, the entropy is even higher, so the slope will be even higher, and the chemical potential will look something like this. The point at which, so this is solid, liquid, and vapor. The point at which the solid line intersects with the liquid line, then the chemical potential of the solid is the same as the chemical potential of the liquid, and this will be the melting temperature, or the freezing temperature if you're coming from the other side. Let's call this point A. Similarly, this point will be the boiling temperature. So this is for a pure system. When you start heating a pure solid, you can find the melting temperature and the boiling temperature. Now we add a solute to this solvent, and then the chemical potential of the liquid is lowered by some quantity. So we will plot it like this. As you can see, this is the solution, and this line was for pure solvent. As you can see, the melting point now is decreased to the point A prime, while the boiling point now is elevated to the point B prime. So as a result of the reduction in the chemical potential of the liquid or the solvent, the freezing point, let's call it, or the melting point, decreases while the boiling point increases. It has been shown empirically that the change or the elevation in the boiling point is equal to some constant multiplied by the mole fraction of the solute. As you can see, the elevation depends on the concentration of the solute, but there is nothing about the identity of the solute. It turns out that this constant K depends on the gas constant multiplied by the boiling point squared multiplied by the heat of vaporization. This can also be written in other forms, where you can write it as Kb multiplied by the molality. Similarly, the depression in freezing point, or the change in the freezing point, is given by a different constant K. Again, this K prime is equal to R temperature squared divided by the enthalpy of fusion or melting. And this can be also written in different ways depending on which measure of concentration is being used. So these are equations for the depression of freezing point and the elevation of boiling point when a small amount of solute is added to a solvent. A typical example of this is when you see salt being sprinkled on the roads in winter, which means that the melting point of ice is depressed. So for example, at -4 degrees, you will still have melted ice instead of solid ice, which makes driving easier. Or you add salt to boiling potatoes so that the boiling point is elevated and you can boil potatoes faster. We can take an example from the book Self Test 3.8 on page 123. And here we are asked to estimate the lowering of the freezing point of a solution made by dissolving about 3 grams of sucrose. This is about 1 cube of sucrose in 100 grams of water. So you're essentially being asked to find the delta TF. So in order to do this, we must find the concentrations first. The equation that we will use is delta Ref equals this constant K multiplied by the molality of the solute, and here we need to find the molality of the solute. So what we have is 3 grams of sucrose in about 100 grams of water, or 30 grams in 1000 grams of water, that's 1 kg of solvent. And the number of moles in 30 grams of water for sucrose is 30 divided by 360, because 360 is the molecular weight of sucrose. So the molality is equal to 30 divided by 360, which is the number of moles in 1 liter or 1 kilogram of solvent. It turns out that this value K, which can be obtained from the book, is 1.86 in the appropriate units, and therefore the reduction in freezing point will be equal to the molality multiplied by this constant, and this is equal to approximately 0.16 Kelvin. So the actual freezing point will become minus 0.16 degrees centigrade. All right. There is another colligative property, which is osmosis, which is more important from the biological perspective. And this is discussed in a separate video. You can look through this video. One of the uses of osmosis is to look at this part after you've gone through the osmosis video. One of the uses of osmosis is to calculate the molecular weight of proteins. So assuming you have looked at the video of osmosis, we will go further. So osmosis says that the osmotic pressure is equal to the concentration of the solute multiplied by RT for an ideal sort of solution, and this can be written in this way as well. It turns out that for real solutions, this equation becomes slightly more complicated, and you have higher order terms and so on. If the concentration is low, remember these terms, for example, this term can drop off. Now, the concentration in terms of molarity is the number of moles of solute per unit volume of solvent. The number of moles is equal to the mass of the solvent divided by the molecular weight divided by the volume, and this is equal to 1 divided by the molecular weight multiplied by mass divided by volume. So remember, this I'm writing as 1 m multiplied by c. This concentration is in kg per metric cubed. So the above equation can be written as osmotic pressure divided by c by m from here equals RT plus this K1, some constant, multiplied by c divided by m. I'm ignoring higher order terms, assuming it's a dilute solution and the concentrations are very low. If I divide the entire equation by m, I get osmotic pressure divided by concentration equals RT by m plus the constant K multiplied by c divided by the molecular weight squared. So what you can do now is you can plot the osmotic pressure divided by C versus C. So you need an instrument where you can measure osmotic pressure as a function of concentrations. This instrument is called an osmometer. And this osmometer is discussed in your book on pages 127 and 128. So when you plot pi divided by C versus C, what you will get is a straight line. So you have concentration on the x-axis and osmotic pressure divided by concentration on the y-axis, and you will probably have some points like this. And you can draw a straight line through these points. And the y-intercept, as you can clearly see in this equation here, is this value. So this value is RT by m. So you can obtain RT by m from this experiment, and from this value you can calculate the molecular weight of the protein. Another application of osmometry or another example of osmometry is when you take a cell and you suddenly put it into a highly concentrated solution of salt, then the concentration of water outside the cell is lower than the concentration of water inside the cell, which results in ultimately the cells bursting. I will show you a video about cells, RBCs, bursting due to osmosis. Another application of osmosis is reverse osmosis, where the osmotic pressure is reversed to purify water in membranes. I will also show you some examples of this, particularly biological examples of this, a bit later in the course.